Okay, Unit 4, Day 2. We're going to talk here about exponential functions, about the growth factor of the exponential function, and a special exponential function called e to the x, our new number e. We have a new set of numbers. We can see that the rate of change is not constant, but that the growth factor multiplied by 2 each time is the same. And so when this happens, when we have a growth factor that's constant, we have an exponential function. Obviously, the growth factor is 2. And as we just said, if the growth factor is a constant, then we have an exponential function. So in this example, I am multiplying by 4 each time to go from one term to the next, so that is exponential. Here, though, the growth factor is not the same from one term to the x, so it is not exponential. Here, in each term, I am multiplying by 1/5 or dividing by 5, so that is exponential. And here, I'm multiplying each term by root 3. That's also exponential. A couple more examples. Here we're multiplying through by 2, therefore this is exponential. So what we did is we saw this is multiplied by 2, multiplied by 2. So if I kept going, multiply by 2, and sure enough, I hit the last term if I multiply by 2. To go from 2 to 1/3, I divide by 6 or multiply by 1/6. Let's see if that works for everything else. I start here, multiply by 1/6, I get here. Multiply by 1/6, I get here. Sure enough, I get the number that they gave me. Multiply by 1/6, I get here. Multiply by 1/6, I get the number that they gave me originally. And sure enough, I'll get to 1/3 if I keep multiplying each term by 1/6, the growth factor. So an exponential function doesn't just have an exponent, because polynomials have exponents, but the exponent is the variable. That's the key. The base changes depending on the problem, but the variable x, the exponent, varies throughout the question. B, once chosen, stays the same for that particular question. If the base is bigger than 1, then we have a exponential function that grows. If we have a base between 0 and 1, like a fraction between 0 and 1, the exponential function goes in this direction. And so greater than 1, it increases. Between 0 and 1, it decreases. Notice we don't talk about a base or a b that's negative. If I raise anything to the 0 power, I get 1. So that point is always going to be on an exponential function. Without shifting, the horizontal asymptote is going to be y equals 0. And both caves face up, or going from left to right, I am always making a left turn. So it's concave up on its domain. And it passes the horizontal line test. We take one or the other, and so it is invertible. It will have an inverse. And that inverse is going to be very special for this unit. So we can see in example 4, all of them are exponential functions. The variable is in the exponent position. The key difference is the b value or the base. We saw that if the base is bigger than 1, it's going to grow like this one. So that's Roman numeral 3. If the b value is between 0 and 1, like a is, it's going to decrease like Roman numeral 2. And if we have the b value of 1, 1 to the first power, 1 for the second power, 1 is never going to change, and so we have a horizontal line, and that's choice Roman numeral 1. So using transformations, you always need a parent graph to start with. So I look at this, and I look at 3 to the x. 3 to the 0 is 1. 3 to the first is 3. So this dotted graph here is my parent graph. We see that it's going to move to the left 1 and down 2. To the left 1 and down 2. So I take this point to the left 1 and down 2. And I take this point to the left 1 and down 2. And I get my new graph. The down 2 is important because the horizontal asymptote starts at y equals 0. If I go down 2, it goes down to y equals negative 2. And the shift left and right doesn't affect the horizontal asymptote. So domain goes forever left and right. Range from bottom up starts at negative 2 and goes up. As we just said, the horizontal asymptote is y equals negative 2. To the left, negative infinity, y is getting closer and closer to negative 2. To the right, y is getting larger and larger, going off to infinity. In B, I'll say that 1/2 to the x is our parent graph or starting graph. So anything to the 0 power is 1. 1/2 to the first is a half. 1/2 to the second is a fourth. But 1/2 to the negative 1, flipping 1/2 over, we get 2. 1/2 to the negative 2, flipping it over and squaring it, we get 4. Okay? And then we shift it to the right 1 and up 3. So I take this point to the right 1 and up 3. Take this point to the right 1 and up 3. Take this point to the right 1 and up 3. Take this point to the right 1 and up 3 off the graph, but it'll help. And our horizontal asymptote that used to be on the x-axis, y equals 0, goes up 3, and now it's y equals 3, and here's our graph. At this point in your careers, if you can draw parent graphs and shift and do transformations, you shouldn't have to make a table. In a way, your parent graph is the table. So our transformation to the right 1 and up 3, left and right forever. The bottom of our graph, oops, let's fix that. The bottom is what? You're right, it's 3. It goes up to infinity. And another oops, we didn't do the transformation. Y equals 3 is the horizontal asymptote. And so going to the left, the graph goes off to infinity. But going to the right, the y value gets closer and closer and closer. Let's fix this to 3. I could have perfect notes, but maybe you'll learn more by the mistakes I make, and you hopefully won't make the same ones.